Bismillahirrahmanirrahim. I am Professor Jamil and you are watching YouTube channel. Today we are going to take up a specific case of the integral transform, and that specific case is known as Laplace transform, whose full name is one-sided Laplace transform. So let's start to and understand what the one-sided Laplace transform is. So one-sided, this has been parenthesized, means written within the round brackets, because these two words are not usually spoken about the Laplace transform. They are taken to be understood. So since we are doing first time, I have written the full name, one-sided Laplace transform. And definition. In general, the integral transform of any function f(x) is equal to a new function with a new variable, no x, new variable t. And this function is known as integral transform. This is the integral transform of f(x), right? Now, what this means, this integral transform has general formula x equal to a to b integration over x k tx, right? This is the formula for I, and this bracket means this I will operate like this on fx and it will give you ft. Now, if this k tx is known as kernel of the transform, and if this kernel is equal to e to the power minus xt, one variable is from the function whose transform is required, and other one is the new variable. X is the old variable and t is the new variable, and your answer is in the t variable, right? And these limits of integration are a from 0 and b is infinity. This means what? This implies, look, your x-axis is always a horizontal line. It has one origin. From this 0 to on the right hand side, the values go up to plus infinity, and from this origin on the left, the values go up to minus infinity. And you are using these values only and not using these values. I put a cross over here. These values are not used, right? And because of these values of x, which are taken from one side of the x-axis, the transform is given a name one-sided Laplace transform. And when kernel is this and limits of integration are one-sided, mean from 0 to infinity, that's positive values of the x-axis, then this integral transform is known as, right, let's write what happens. This implies x from 0 to infinity dx, and in place of this k you are writing e to the power minus xt like this, and next is fx and it is f of t. This equation is known as Laplace transform. Now this ft, which was integral transform, now this is known as Laplace transform of fx. So this is the definition of Laplace transform. This definition can also be written in a tidier notation. Look, this operator is written as L, and if you have a careful look on this integral, forget for the moment this is what is in the brackets. There are two variables like this. One variable x will be integrated, and in this place you will have some function of t. So this operator, whose name is L, is actually a function of t. This t is not usually written, and it operates on fx and gives you a new function, right? So this is this R. This is L acting on fx and giving you a new variable, and with a new function of new variable. This is the most common notation, and you should understand this is fx, the independent variable of the function whose transform is required vanishes in your answer, and the new variable is in fact the variable which generates your operator L. And this t is more visible in this notation, but unfortunately this notation is not more common. So you should in the first place remember this and this, right, and this. This is the most common definition of the Laplace transform. Now this Laplace transform has I will for the most part of the time use this and understand this L is a function of t like this. Okay. Now this definition has a property which is known as linearity. Let's check what this linearity means. So this property, let me write linearity of Laplace transform, and I am writing one more word, and that is operator, and within the brackets means this word is usually omitted. So when you call linearity, that linearity of the Laplace transform means linearity of the Laplace transform operator. Operator means L. The property is of the operator L. So let's check what is this property. By definition, any operator or function, any operator or function A is said to be linear if A alpha u plus beta v is equal to alpha into au plus beta into av, where alpha and beta are constants, right? Whatever are u and v, they may be functions of any kind, what not and what not. If A operates on u and v and the constants remain as such, then A is known as a linear operator. Linear means this: the power of alpha is 1 and the power of u is also 1. So 1 and 1. The power exponent or power of the symbol 1 means linearity. Okay, so you remember this relation and you can name it as equation number 1. Now we need to check the linearity of the operator which is known as Laplace transform operator L, right? So therefore take A as L, and since this is a transform, so its action will be represented by curly bracket as per the decision of the notation, and this is some constant, and you instead of you have some function f1x plus beta, and instead of v you have some other function f2x, right? And let's simplify this and check whether we get this or not on the right hand side. This is the definition of linearity, and we have used left hand side for our operator L. Now this L means x0 to infinity dx e to the power minus xt. This is the operator, and it act on this alpha f1x plus beta f2x. This is the definite integral. It contains variable x, which is the variable of integration. So this bracket can be made part of the integrand, that is x equal to 0 to infinity dx. The integrand is e to the power. After you have applied the operator, then do this whole job just as you are doing in your integrals, normal integration, right? So this is ex into alpha f1x plus beta f2x. And now you can expand this bracket, mean normal integration, apply the rules of integration wherever you need. So this will be dx into e minus xt into alpha f1x plus e minus xt into beta f2x. Now you can multiply dx throughout, and let's do this on the other board. Let me do this here. L of alpha f1x plus beta f2x, and it is equal to, look, this is integral dx multiplied by this one, integral dx, and this dx into e to the power minus xt and alpha f1, e to the power minus xt into alpha into f1x plus, you are in fact expanding this bracket. This dx will be multiplied with this one, right? So x0 to infinity dx minus xt and beta f2x, right? This thing. This is multiplied with this one, e to the minus xt into beta f2, e to the minus xt into beta f. Now, this alpha is a constant, beta is also a constant. They do not depend on x or t, so they can be taken outside the integral sign. So as alpha and beta are constants, that is, alpha and beta do not depend on x and t, so they can be taken outside the integral sign. So on the left you have alpha f1x plus beta f2x equal to, this alpha is out, and you have x0 to infinity plus beta and 0 to infinity dx e to the minus xt into f2x. Now you can look this equation as, this is alpha and this is your operator 0 to infinity, and it is acting on f1x plus beta, and this integral is acting as an operator dx e to the power minus xt, and it is operating on f2x. And this is what? Look, this is your operator L. So alpha into L acting on f1x plus beta, and this is L operator acting on the function f2x. And on the left hand side you have L operator acting on alpha into f1x plus beta into f2x. And look, this is the same as your equation was alpha of L1. Instead, in place of A, your operator is L, and in place of U, your function is f1, and similarly for this. So this is similar to definition of linearity in equation 1. Hence, the operator L, hence the operator Laplace transform operator, hence Laplace transform operator is a linear operator, or we can say that Laplace transform operator has linearity, right? And look, the word operator has been parenthesized, mean written within the brackets, because this word is not usually spoken, and people say Laplace transform has linearity. So Laplace transform, whenever you mean has some property, that means operator, the Laplace transform operator has property. So, and remember, this is a very, very important property, and with the help of this property, many difficult jobs can be done quite easily. Listen again. This property of linearity in the Laplace transform operator is of extreme utility for turning difficulties or impossibilities into eases. Thanks for watching. Please like, share and subscribe, and above all press the bell icon so that my every new lecture happens to be in your inbox or in your cell phone in the first place. Thanks for watching. Keep watching my videos.